Hello everyone, this is the video series on OPAMP by Professor T. Square. In the first video, we have learned the basics of OPAMP. We have learned what is inverting terminal, what is non-inverting terminal, and also we have solved some numericals which was asked in CSIR-UGC NET and GATE exam. This is the second video. In this video, we are going to learn about closed loop configuration, summing amplifier, and OPAMP circuits with resistors and capacitors. If you're watching the series video for the first time here, I recommend you to watch the videos in sequence for better understanding. Okay, now let's start. Now let us discuss closed loop OPAMP. Before going to closed loop OPAMP, we will discuss what do you mean by closed loop. A system is said to be in closed loop if there is some kind of a feedback mechanism. So if I consider a system here, let's say this is a system. This is a system and I have an input here. I'll call it V in. Then because of the system dynamics, we'll be getting an output here. And what I'll do is I'll take the output and I will feed this output to another circuit. This is called as the feedback circuit. And from the feedback circuit, some portion of the output will be fed to the input terminal. And the fraction of the output which is fed to the input terminal, we call it VF, the feedback signal. Now, because of this, the effective input to the system will be different. I'll call this as Vx. The Vx is the effective input given to the system. Now, depending on the relation between the Vf and Vin, suppose if Vf is in phase with the Vin, the input signal, then we call it this to be positive feedback. And if Vf is anti-phase, or you can say out of phase with Vin, then we call the feedback to be negative feedback. So this is a concept of feedback, and by checking the relation between Vf and Vin, we can identify whether it is a positive feedback or negative feedback. Let us consider this system here. This is an OPAMP circuit. Now, some portion, the output, if you see here, the output is connected to the input through a network of resistors. So this is a closed loop OPAMP. Now, to identify whether this is a positive feedback or negative feedback, now the voltage at this point, I'll call it Vx. So some signal is going inside to this OPAMP. Now, correspondingly, we'll be getting the output. Now, if you see carefully, the Vx, the output due to Vx will be inverting. That is because why it is inverting? Because the Vx is fed to the inverting terminal of the OPAMP. So the output which you will get will be inverting. Now this inverted signal, I'll just write it down here. Inverted output. Now this inverted output is fed to the input terminal. And if I try to compare this Vx and V0, that is the V output, it is inverted with respect to Vx. So it will be negative feedback. The best way to identify whether it is a positive feedback or negative feedback is if you want to identify whether it is a positive feedback or negative feedback is, check where the feedback signal is given in the input terminal. If it is given in the inverting terminal, then you can directly say it's a negative feedback. If the feedback signal is given in the non-inverting, then you can say it's a positive feedback. Most of the numericals on OPAMP are based on negative feedback, but some few questions are also asked where they have used the positive feedback. At the end of this video, we'll be discussing numericals on positive feedback also. Closed loop OPAMP can be classified into two types. One is non-inverting and other one is inverting. So to identify whether it is a inverting or non-inverting, we need to see the network architecture. In this circuit, the first thing which we can observe is the output is connected to the input. So it is a closed loop. And the input is given at the inverting terminal and the other one is grounded. So this is a closed loop non-inverting OPAMP. Now to find out the output, we need to apply two concepts. The first one is the golden rule, which we have discussed a few minutes ago. So if we call this voltage as Vx, so as according to the golden rule, we can write Vx is equal to Vi. The second concept is the input impedance is very high, so no current will enter into the OPAMP. So if I assume that the current flowing here is I, then the current flowing through R1 is I, then we can say then the same current will also flow through RF. That means no current will be going into the OPAMP. So if this is I, that is the current flowing to R1, then the same current will also flow through RF. So using this concept, let us consider this portion of the circuit. You have R1 here, then RF here, and this is connected to V0. So here at this point the voltage is Vx and here it is 0 volt. So if I consider the current through R1 is I1 and the current through RF is I2, then we can write I1 is equal to I2. So I1 can be expressed as 0 minus Vx by R1, which is equal to, and I2 can be expressed as Vx minus V0 by RF. Now, if from this expression we can write V0 by Vx is equal to 1 plus RF by R1. Now, from the golden rule, we already know that Vx is equal to V in. So we can write this as V naught by V input. So that is V naught is equal to 1 plus RF by R1 into V input. So this is the expression of the output in the case of closed loop non-inverting op-amp. Now in the given circuit, the output is connected to the input, so it's a closed loop, and the non-inverting terminal is grounded and input is applied to the inverting terminal. So this is a closed loop inverting op-amp. Now let us try to calculate the output of this. So using the golden rule, the same current will be flowing in this part, and this voltage is 0 volt, and I will take this one as Vx. So we can write Vx is equal to 0 volt. Now let me redraw this diagram here. So you have V input here, R1, then RF here, and this is connected to V naught. So if this is I1 and this is I2, then I can write I1 is equal to I2 and this voltage is Vx. So I1 you can express as Vi minus Vx by R1. This is equal to I2 is Vx minus V naught by RF, and Vx is 0, so I can rewrite this expression as R1 is equal to minus of V naught by RF. So V naught is equal to minus RF by R1 into V input. So this is the expression of the output in the case of closed loop inverting terminal. Now let us try to recall the two formula. For closed loop, if it is inverting, then V naught is equal to minus RF by R1 into V input. And if it is non-inverting, then V naught is equal to 1 plus RF by R1 into V input. Now using these two formula, let us solve some numericals. This question was asked in GATE 2019. We are given a circuit here. We have to find out the output given the input is 1.5 volt. So the first thing we have to identify is whether it is an inverting or non-inverting. Now here we can see that the non-inverting is grounded and the input is given here. So this is a closed loop inverting op-amp. We know the formula of this. We know the formula of the output. V naught is equal to minus RF by R1 into V input. Now this resistor R, this is the R1 and this one is RF. So if we substitute their values, it will be 100 R divided by R into 1.5, the input. So if we do the calculation, this will give 150 volt. Now the answer is not 150 volt because here we can see the supply is plus minus 15 volt. That is V supply is plus minus 15 volt. Now we have already learned that the output cannot exceed the supply voltage. So the closest answer will be, if I take the magnitude, it will be 15 volt. So option C is the correct answer. This question was asked in CSIR-UGC NET 2015. We are given a circuit and in the feedback part, there is a thermistor whose resistance at 25 degrees Celsius is 3 kilo ohm, and coefficient of resistance is 150 ohm per degree Celsius. We are told to find out the output voltage at the circuit at 30 degrees Celsius. Now, if you see this circuit, the non-inverting is grounded and input is given here. So it is a closed loop inverting op-amp. And we already know the expression of the output. This is minus RF by R1 into V input. Now R1 is already given 1K. We have to find out RF. Now thermistor is a semiconductor type resistor. So in such type of resistor, when we increase the temperature, resistance will decrease. So using the basic semiconductor, we can find out the resistance at 30 degrees Celsius to be equal to resistance at 25 degrees Celsius minus the coefficient of resistance 150 into the difference in the temperature, that is 30 minus 25. So if we substitute this, you can do the calculation. R at 30 degrees Celsius will be 2250 ohm. And this is the RF at 30 degrees Celsius. Now we have obtained RF, so output is minus RF by R1 into input. So minus 2250 divided by 1 kilo ohm. So 1000 ohm into, now see the input is minus 1. So if we do the calculation here, we will get 2.25 volt. So option C is the correct answer. This question was asked in GATE 2015. We are given an op-amp circuit. We are told to find the feedback configuration and the closed loop gain. Now, if we see this circuit, the input is given to the non-inverting terminal and the inverting terminal is grounded. So it is a closed loop non-inverting op-amp, and we already know the expression of the output 1 plus RF by R1 into V input. And the next thing is we need to identify which one is RF and which one is R1. Now the output V0 is taken across this resistor RL. So this 9 kilo ohm is the RF and 1 kilo ohm is the R1. So if we now we are asked about the gain, so we can write the gain as V0 by V in. So this is equal to 1 plus RF by R1. So if we substitute the values, we 1 plus 9 kilo ohm divided by 1 kilo ohm. So after solving this, we can get AF is equal to 10. Now, for the feedback configuration, we need to understand the nomenclature. The nomenclature of the feedback nomenclature. So, nomenclature. Now, the feedback nomenclature, we write like this: the information of the input and the information of the output. Here, when I say input, it is giving the information that what type of input signal is given, whether it is a voltage or a current. And here in the output, it says the information of what type of output signal is taken, whether it is a voltage or a current. Suppose if the input is a voltage, then it will be written as series. And suppose if the input is current, then it will be written as shunt. Similarly, for the output, if the output signal is voltage, then it will be written as shunt or parallel. And if the output signal is current, then it will be written as series. So let us take one example. Let's say we call it series shunt feedback. So that means in this series shunt feedback, it is saying that the input is in terms of the voltage signal, and the output is in terms of voltage. Similarly, if we take series, that means the input is voltage and the output is current. Now let us come back to our circuit here. Here the input is voltage. So the input is voltage. So in the input, it will be series, and the output is also voltage. So it will be shunts. So the answer to this question is, the feedback is a series shunt feedback. So this is the type of feedback used in the circuit. Now these are the two answers. So if we see the option, okay, we can see the option C, series shunt feedback with a closed loop gain of 10. So this is the answer. Now this question was asked in GATE 2017. We are given an OPAMP circuit and they have given the values of R1, R2, RL. The input is 10 millivolt and we are told to find the current passing through R2. Now, the first thing, suppose if the voltage here is Vx. So by using the golden rule, we can write Vx is equal to V in. And the same voltage will be also at this node. It will be Vx. Now, the second concept is no current will be flowing in this branch because the input impedance of op-amp is very high. So whatever the current flowing through R1, the same current also will flow through R2. Suppose if I call this one as I1 and this one as I2, so I can write I1 is equal to I2. Next, the voltage at this terminal will be 0 volt. So I2 will be equal to Vx minus 0 by R2, and Vx is equal to V input, so it will be R2. So if I substitute the value 10 millivolt divided by 1 kilo ohm, so the answer is 10 microampere. This question was asked in CSIR-UGC NET 2016. We are given an op-amp circuit and they have given the voltage, the power supply, R2, RL, and we are told to find the value of R1 so that a power of 10 milliwatt is delivered across the load resistor. So we can identify this, we can name this voltage as Vx. The same voltage will be here at this node. So Vx is equal to V input by using the golden rule. Similarly, if this is V naught, then the same voltage will be at this node V naught, and here it will be 0 volt, 0 volt. Now we have identified the voltage at each node. The second concept is, since the input impedance is very high, the current flowing through R2 will be the same as the current flowing through R1. So I'll call this one as I2 and this one as I1. So I1 will be equal to I2. I1 is 0 minus Vx by R2, and I2 is Vx minus V0 by R1. And we know that Vx is equal to Vi, so we can substitute this like this, R2. So Vi minus V0 by R1. Now, to solve this equation, we need to know the V input, which is already given. We know R2, which is given, but we don't know V0. So to calculate V0, we will use the information of the power. So power at load is equal to V0 square by RL. So V0 square is equal to the power into the load resistance. So if we substitute 10 milliwatt into RL is 10 kilo ohm. So from here, V0 square is 100. So V0 is equal to 10 volt. So now we can substitute in this expression. Input is how much? 2 volt. R2 is 2 kilo ohm. Then 2 minus 10 divided by R1. Now if you solve this, you'll get R1 is equal to 8 kilo ohm. So this is the answer. So option C. Till now, whatever closed loop op-amp we have discussed, we have given input at one terminal and the other terminal was grounded. But in this circuit, you can see that there are two inputs, V1 and V2. Such type of closed loop op-amp, we call it difference closed loop op-amp. Now, let us learn how to calculate the output. So using the golden rule, we can say if I denote this voltage by Vx, so we can write Vx is equal to V2. Next, the current flowing through R1 will be the same as the current flowing through RF because of high input impedance. So if I call this one as I1 and this one as I2, so I1 will be equal to I2. So I1 we can write as V1 minus Vx by R1. I2 we can write as Vx minus V0 by RF. Now Vx is equal to V2, so we can substitute that. So V1 minus V2 divided by R1. This is equal to V2 minus V0 by RF. Now you can pause the video and do the calculation, and you can find the final expression V0, that is the output. This is equal to 1 plus RF by R1 into V2 minus RF by R1 into V1. So this is the expression of the output. Now, this is the proper way to do it, but here I will teach you the shortcut. Now, for the shortcut method, see how many inputs are there. There are two inputs. One is V1, other one is V2. Now, you first calculate the output due to V1 when V2 is grounded. So let's take this circuit. So what I'll do is I will ground this V2 and I'll calculate the outputs. I'll call as V01. So V01 is the output when V2 is grounded. So if you see this circuit is a closed loop inverting op-amp. So V01 will be equal to minus RF by R1 into V1. So this is the output. Next, you take the same circuit. Now you ground V1. So I'm grounding V1. And you calculate the output due to V2 alone. So I'll call this as V02. So if you see this circuit is a closed loop non-inverting op-amp. So the output will be given by 1 plus RF by R1 into V2. So now you have got two output here. Next, the final output V0 will be the sum of V01 plus V02. Now if you substitute these two output, and you can find that both the expressions are the same. So this is the shortcut. Now let us try to find the output for this circuit, and you can see there are two inputs, V1 and V2. So we can use the shortcut here. So there are two inputs, V1 and V2. So first let us calculate the output due to V1 when V2 is grounded. So I will ground this V2 and let the output be V01. So this circuit is a closed loop inverting op-amp. And you can see the voltage here is 0 volt. Here also it will be 0 volt, and here 0 volt. So for closed loop inverting op-amp, the output is minus RF by R1 into V1. Okay, now let us see for V2. So I will ground V1. And please note this, V2 is applied here, but the net voltage which is applied at the non-inverting terminal of the op-amp is the voltage at this point. So we need to calculate the voltage at this point. So I'll just call this as Vx. So Vx is equal to, you can use the voltage division rule. So R3 divided by R2 plus R3 into V2. Now for this Vx, this circuit is closed loop non-inverting. So the output V02. So yeah, we can write here V02. This is equal to 1 plus RF by R1 into, see, here it will be Vx, not V2, because Vx is the voltage applied at the non-inverting op-amp terminal. So we can write V02 as 1 plus RF by R1. Now we can substitute the expression of Vx, that is R3 divided by R2 plus R3 into V2. So this is the expression of V02. Now we have got both V01 and V02. So the net output will be the sum of V01 plus V02. So V0 is equal to minus RF by R1 V1 plus 1 plus RF by R1 into R3 divided by R2 plus R3 into V2. So this is the final expression. This question was asked in CSIR-UGC NET 2016. Here we have two inputs. One is constant of 0.5 volt and other one is a time varying signal V in, whose graph is given here. So this is a time varying input voltage. Now we are told to find out the waveform of the output. So this circuit is similar to what we have discussed few moments ago. Now I will call this 10K as RF, this one as R1, this as R2, and this as R3. And this one I can call it V1 and this one is V2. So first we will calculate the output due to V1 when V2 is grounded. So V01 will be equal to minus RF by R1 into V1, which is nothing but minus RF by R1 into Vin. Next, we will calculate the output when V1 is grounded. So for that, we need to calculate this Vx here. Vx. So Vx is equal to R3 divided by R2 plus R3 into V2. V2 is 0.5. So we can write 0.5 here. So R2 by R3 into 0.5. Now the output due to V2 will be equal to, so 1 plus RF by R1 into R3, R2 plus R3 into 0.5. So the net output will be given by V01 plus V02. Now you can pause the video and substitute the value of R1, RF, R2 and R3, and you'll get a final expression of V0 is equal to 1 minus 2 of V input. See, V2 is constant, but V in is varying with time. So using this information, we can predict the output wave pattern. So let us come back to this input plot. So I will call this point as A, this is B, this is C, and you can call this as D. So at point A, V in is 0. So when V in is 0, your corresponding V output will be 1. At point B, V in is 0.5. So when V in is 0.5, you can substitute and you can find that it is V0 is 0. At point C, again V in will be 0, then V output will be 1. Similarly, at point D, V in will be minus 0.5. So if we substitute minus 0.5, then you will get V0 is equal to 2. Now, using this information, we can plot the graph. Suppose if this is, let's say, 1 and this is 2 and this is 0. So at point A, the output will be 1. Maybe I can draw a line here so that it will be easy to plot. So I'm drawing this line. So at point B, the V0 is 0. So it will be 0 here. At point C, that is at V in equal to 0, V0 is 1 again. And at point D, when V in is minus 0.5, V0 is equal to 2. So now we can draw the output pattern, it will look something like this. So this is the answer. Now we will discuss summing op-amp. In summing op-amp, multiple inputs through resistors will be applied to inverting terminal, or multiple inputs through resistor will be applied to non-inverting terminal. Now let us try to learn how to find the output of such type of circuit. Now here the voltage here is 0 volt, so similarly here also it will be 0 volt, and whatever the current flowing here, the same current will be flowing through RF. So if I call this current I, then let's say the current flowing through this branch is I1, the current flowing through this middle branch is I2. Similarly, the current flowing through this is I3. Then I1, I2 and I3 will combine and give I. So I is equal to I1 plus I2 plus I3. Now I1 we can express as 0 minus V0 by RF. I1 we can express as V1 minus 0 divided by R1 plus I2 V2 minus 0 by R2. Similarly, I3 V3 minus 0 by R3. Now we can rearrange this term and we can write V0 as minus RF by R1 into V1 plus RF by R2 into V2 plus RF by R3 into V3. So this is the expression of the output. Now we can arrive to this formula by using a simple trick. We can write the output as, there are three inputs, V1, V2 and V3. Now you ground V2 and V3 and apply the input only at V1. So when we apply the input at V1, it is a simple inverting closed loop op-amp. So the output will be minus RF by R1 into V1. Next, you ground V1 and V2. You ground V1 and V2. Then you apply, you ground V1 and V3. Then you apply the input at 2. So for that, the output will be minus RF by R2 into V2. Similarly, you ground V1 and V2, then apply the input at V3. So the output will be minus RF by R3 into V3. So if you see carefully, these two formulas are the same. Now, coming back to the second circuit. Now here the inputs are applied at the non-inverting terminal, but there is a negative feedback here. So for this, the voltage here will be 0 volt, and let us call the voltage here as Vx. And now we know that the input impedance of op-amp is high, so no current can go into the op-amp. So if the current flowing here is I1, if the current flowing here is I2, then since the current is not going into the op-amp through the non-inverting terminal, so I1 plus I2 should be equal to 0. Now suppose if there are three terminals, then it will be I1 plus I2 plus I3 equals to 0. Now the voltage at this point will also be equal to Vx. So I1 we can write as V1 minus Vx by R1 plus I2 we can write as V2 minus Vx by R2 equals 0. Now what you have to do is, from this expression, you find out Vx. So Vx will be equal to, you can pause the video and do the calculation. So I'm writing the final expression here. It will be R2 R1 plus R2 into V1 plus R1 divided by R1 plus R2 into V2. Now after finding out the expression of Vx, now you come to the other branch. So here, whatever the current flowing here, the same current will be flowing through RF. So if I call this as, let's say, I3 and this one as I4, then we can write I3 is equal to I4. Then what is I3? I3 is 0 minus Vx by R1 equals Vx minus V0 by RF. So from this expression, you can get V0 is equal to minus RF by R1 into Vx. Now, in the output expression, you substitute this Vx here. Then you can get the final expression of the output. And this is how we deal summing op-amp, where the inputs, multiple inputs are applied in the non-inverting terminal. Now, this question was asked in GATE 2018. We are given a summing amplifier with inputs V1 and V2. V1 is given as 1 volt, V2 is given as 2 volt. And the output V0, we have to find the output, and this output is measured across the load resistor RL. Now, we know the formula of V output, that is minus RF by R1 V1 plus RF by R2 into V2. Now, this is R1 and this is R2. So if we substitute here, RF is 4, R1 is 2 into 1 volt plus 4 RF, R2 is 5 into 2 volt. So this cancels out 2, and so V0 will be equal to minus 2 plus 1.6. So you get V0 is equal to minus 3.6. This is the answer. This question was asked in CSIR-UGC 2020. Now, compared to the previous circuits which we had discussed, this circuit is different because there is a capacitor here. And in this circuit, a sinusoidal voltage is given as an input with a frequency of 100, and we are told to find the phase difference between the input and the output. Now, whenever capacitor is there, we have to replace the resistance with the reactance of the capacitor. That's the only trick. Now, in this circuit, here the resistor, I will call this as R and I will call this as C. Now, these two are in series. So, the effective impedance of these two will play the role of R1. So R1 will be equal to R plus XC, and this 4 kilo ohm, this is the RF. Now, here XC is equal to 1 by J omega C, where J is for the imaginary number. Now, the gain, if you see this circuit is a closed loop inverting op-amp. So, V naught is equal to minus RF by R1 into V in. Now, this is the formula which we know. So, for this situation, V naught will be equal to minus RF by R plus XC into V in. So, we can write V naught by V in is equal to minus RF is equal to 4 kilo ohm and R is equal to 2 kilo ohm and XC is 1 by J into omega. Omega is 100 into C is 5 microfarad. So 5 into 10 to the power minus 6. Now, you can pause the video and do the calculation. I will write the final expression here. V naught by V in will be equal to minus 2 divided by 1 plus 1 by J. Now, 1 by J, we can rewrite this expression like this. Now, see, the relation between the output and the input is a complex number now. So, what we have to do is, we have to express in the polar form. So, V naught by V in is equal to 2 into 1 minus J, we can express in polar form. So, it will be e to the power minus J pi by 4. So, one more minus is here. So, it will be minus root 2 e to the power J pi by 4. Now, this minus 1 we can express as e to the power minus e to the power J pi into e to the power J pi by 4. So, this one, if I sum the two exponent, then it will be e to the power J 5 pi by 4. Now, let me write the final expression. So, V naught by V input is equal to root 2 times e to the power J 5 pi by 4. So, this is the relation between the output and input. So, if you see this portion, this is the phase difference. So, the answer is 5 pi by 4, option A. Now, this question was asked in GATE 2020. If you see the network architecture, you have a V input applied to both the terminals. So, basically, this is a difference amplifier. And the difference with the circuit which we have analyzed before is that here we have a capacitor instead of a resistor. And in the question, it is the input is given and the expression of the output is also given. And if we compare the two expression here and here, we can see there is a phase difference of minus pi by 2. Now, here the input here is VI. Here also it is VI. I will call this one as V1. I'll call this as V2. And this R is equivalent to R1. This one is equivalent to RF. I'll call this as R2. And instead of R3, we will have XC, which is equal to 1 by j omega C. Now, if we use the trick which we have learned, the output will be equal to, okay, first you ground V2. So when you ground V2, the output contributed by V1 will be minus RF by R1 into V1. Then next, the contribution from V2 when V1 is grounded, it will be plus 1 plus RF by R1 into the voltage at this point, this is Vx. So it will be Xc divided by Xc plus R2 into V2. Now you can pause the video and you can substitute R1, R2, RF, Xc, V1 and V2. Please note that V1 and V2 is V input. So after the substitution, you will get an expression like this. V naught by V in is equal to 1 minus, actually it should be minus 1 minus j omega CR divided by 1 plus j omega CR. Now, the relation between the output and input, it is in a complex form. So you can express in polar form. So if I express in polar form, it will be 1 plus omega CR whole square divided by 1 plus omega CR whole square. And for the numerator, it will, I'm just denoting the phase by theta here, and here also you'll have j theta, where theta is equal to tan inverse of omega CR. Now, these two will cancel out. So, V naught by V in is equal to e to the power minus j 2 theta. Now, this minus 2 theta is the phase difference between the output and the input. And from the question, we already know that there is a phase difference of minus pi by 2. So, minus 2 theta will be equal to minus pi by 2. Now, if we substitute minus minus, we can cancel. So, 2 tan inverse omega CR is equal to pi by 2. Now, R is already given. R is given as 1 kilo ohm. R is already given 1 kilo ohm. C we have to find out. Omega is already given in the expression of the input as well as in the output. Now you can use this equation. You can use this equation to find out the value of C. So you can pause the video, do the calculation, and you'll get C is equal to 10 microfarad. So option C is the correct answer. Now these are two types of circuits where capacitor is used. Here you can see that there is a capacitor in parallel with a resistor. And in this network, there is the input is fed to an RC network. Then it goes to the non-inverting terminal. Now let us learn how to calculate the output. Suppose if this 1 kilo ohm will denoted by RF and the reactance of this capacitor R will denoted by XC. So the effective reactance will be, I'll denote it by X. X is equal to RF in parallel with XC, where XC is equal to 1 by j omega C. Now, if this resistance is R1, then output will be equal to minus X divided by R1 into V input. Here X is RF parallel to XC, which can be written as RF into XC divided by RF plus XC. Now, the final expression of the output will be minus of RF XC divided by RF plus XC into R1 into V input. So this is the expression. Now, depending on what is asked in the question, suppose if they are asking about the phase difference, then you have to derive this expression V naught by Vi and you convert it into the polar form. You convert it into the polar form. If they are asking about the gain, then you can take the magnitude, then this will be equal to the closed loop gain. Now let us come to the next circuit. Now, if you are familiar with electronics, this RC network, this is a kind of a filter. So the input is fed to a filter and the output of the filter is fed to an OPAMP. So sometimes they can ask about the cutoff frequency. Now the cutoff frequency will not depend on these two resistors, it will depend on this RC network. If I draw this RC network here, so this is the input and this is R and this is C. So if a signal comes here, now the capacitor, the impedance, the reactance of a capacitor is 1 by j omega c. So when omega is tending to 0, when omega is low, xc will tends to infinity, and when omega is tending to infinity, that is at high frequency, xc will tends to 0. So the signal which is coming, if it contains a high frequency, then the high frequency will go towards this branch and only the low frequency will be transmitted. So basically this is a low pass filter. Now for this low pass filter, the cutoff frequency will be given by 1 by 2 pi RC. So if they are asking about the cutoff frequency, then you have to use this portion of the circuit. Now this signal will be fed and it will be amplified, and if you see the OPAMP portion, it is nothing but a closed loop in non-inverting OPAMP. So in this question we are given a circuit and we are told to find which type of filter is this. Now C2 is in parallel with R1, so the effective impedance will be R1 in parallel with the impedance of C2. Now here what we can do is I'll just denote the impedance by X2, so the effective impedance will be R1 in parallel to X2, and let the impedance of this C1 be X1. So we can write the output as minus R1 in parallel to X2 divided by X1 into V input. So V naught by V input is equal to minus. Since R1 and X2 are parallel, so we can write the formula for parallel combination. So this is the expression. Now here X1 is nothing but 1 by j omega c1 and X2 is 1 by j omega c2. So you can pause the video, substitute the expression of X1 and X2, then you will find that V naught by V in is a complex form. This will be a complex form. So what you can do is you can reduce it to polar form and you can consider only the magnitude. So I'm writing the final expression here. So V naught by V in is equal to omega C1 R1 divided by root over 1 plus omega square C2 square R1 square. So this is the magnitude. Now we can rearrange this term and express as V naught by V in magnitude will be equal to C1 R1. So I am simplifying this term, and this one will be 1 by omega square plus C2 square R2 square. So using this formula, we can identify which type of filter is this circuit. Now in this expression, if I put omega tending to 0, then V naught by V input will tend to 0. That is, at lower frequency, the gain is tending to 0. What about when omega is tending to infinity? Then in that case, V naught by V in will tend to so C1 by C2, which is a constant. So at higher frequency, the gain is constant, and at lower frequency, the gain is tending to 0. So basically, the circuit is behaving like a high pass filter. So option A is the correct answer.